Hello students, welcome to the EPG Pathshala. I am Ashok Goel from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the Hamiltonian formalism and Poisson bracket. In fact, we'll continue. In the last unit also we talked about this, but now we will illustrate what we have learned with the help of some examples. All this from the paper Classical Mechanics. So let us see what we are going to learn in this module. So we'll take up some representative problems and we'll solve them in order for you to become familiar with the Hamiltonian and Poisson bracket formalism in classical mechanics. In this unit, we will illustrate the formalism which was developed in connection with the Hamiltonian dynamics and Poisson bracket with some representative solved problems. Let's consider a few problems. Let's consider first the problem of a charged particle which has a charge E and mass m and is moving in a constant magnetic field. Let the magnetic field be along the z direction. So we are supposed to set up the Hamiltonian of the system and solve the equations of motion and find out what are the conserved quantities of the system. The problem we are considering is not just the problem of a charged particle in the magnetic field, in the presence of electromagnetic field. We have the electric field also present. So, the Lagrangian in the presence of electromagnetic field is given by, as we know from our earlier units, that L is equal to half m x dot square plus y dot square plus z dot square minus E phi plus E by C A dot V, where E is the charge, phi is the scalar potential and A is the vector potential. In the present case, if you consider the motion to be purely in the magnetic field, that phi is equal to 0, and since the magnetic field B is given by curl of A and we assume the magnetic field B to be along the z direction, then this magnetic field in the z direction can be derived from a vector potential which is simply equal to half the vector product of B with R, which gives us the vector potential A is equal to minus half B times Y unit vector I plus half B times X a unit vector G. That is a vector potential in the direction of Y and X with a fixed component value half B gives me the desired magnetic field in the Z direction. Having written down the Lagrangian for a charged particle in the presence of electromagnetic field, we can obtain the conjugate momenta from the usual relation using Lagrangian, that is Pi is equal to dl by dqi dot, and construction of Hamiltonian is then straightforward, and the Hamiltonian that we obtain for a charged particle is equal to 1 by 2m px plus eb by 2cy whole square plus py minus eb by 2cx whole square plus pz square. Now what we want to do, having obtained the Hamiltonian, we want to write down the Hamiltonian equations of motion. The Hamiltonian equation of motion we are all familiar with, and straightforward now. Our coordinates are x, y, z and our conjugate momenta are px, py and pz. So the equation of motion can be immediately written and we get, for example, x dot is equal to px by m plus e by b divided by 2mcy, and the equation for y dot is equal to py by m plus e by 2mcx and z dot is equal to pz by m. And for another set of equation, conjugate equation, we can combine this together, and finally the set of equations that of motion that we get are x double dot is equal to eb by mc y dot and y double dot is equal to minus eb by mc x dot and z double dot is equal to 0. These are the same equation which we have obtained earlier. We now consider a Hamiltonian which is given as Q1 P1 minus Q2 P2 minus A times Q1 square plus B times Q2 square, where A and B are constant, and Q1 Q2 are two generalized coordinates with their conjugate momenta P1 and P2. Using the Hamilton's equation, the problem we want to consider is to show that a function f1, which is defined as p2 minus bq2 by q1, and a function f2, which is defined as a product of q1 q2, and a function f3, which is defined as q1 into e to the power minus t, are all constants of motion. Now, how do we go around this problem? So, from the Hamiltonian, the Hamiltonian equations therefore are dH by dpi is equal to qi dot, and dH by dqi is equal to minus pi dot, and dH by dp2 we now write for p1 and p2. So the equations that we obtain are q1 is equal to q1 dot minus q2 is equal to q2 dot, p1 minus 2a q1 is p1 dot, and minus p2 plus 2ab q2 is equal to minus p2 dot. Having defined f1 and f2, let us look at the time derivatives of f1 and f2. So df1 by df2, for example, is equal to p2 dot minus bq2 dot divided by q1 minus p2 minus bq2 by q1 dot. And now substituting for p2 dot and q2 dot and p1 dot and q1 dot, etc. from the Hamilton equation of motion, we can see that df1 by dt is equal to 0, and likewise we have df2 by dt is equal to 0, and df3 by dt is also equal to 0. Therefore, f1, f2, f3 are constants of motion. Example 3, we will consider a Hamiltonian system with only one degree of freedom, and if the Hamiltonian is given by p square by 2m plus some function a of q multiplied by b plus some function b of q, where a and b are functions of coordinates q and p is the conjugate momenta. We want to obtain the Lagrangian of the system and calculate the Poisson bracket of q and p with the Hamiltonian. Now, from the Hamilton's equation, it's straightforward to see that q dot, which is equal to dH by dp, is equal to p by m plus aq, and likewise minus p dot is equal to p into partial derivative of a with respect to q plus partial derivative of b with respect to q. And now, since the Hamiltonian is pq dot minus L, therefore L is equal to H, L is equal to pq dot minus H. And substituting for H and for q dot from the equations of motion, we obtain L is equal to a term which is given in the last line, which can be simplified to give L is equal to p square by 2m minus b of q. We have the Poisson bracket between q and h is the Poisson bracket between q, which and h is p square by 2m plus a times p plus b. And using the property of the Poisson bracket, this can be written as p by m, a Poisson bracket of q with p plus a, the function a of q, multiplied by the Poisson bracket of q with p. Now, Poisson bracket of q with p is unity, and Poisson, therefore, this is simply p by m plus aq, and which is equal to q dot from the equation. Therefore, we can calculate the Poisson bracket of p with h also, and which is p dot. So, we simply have the relations that Poisson bracket of q with h is q dot, and the Poisson bracket of p with h is p dot. As another problem, let's consider a system with n degrees of freedom. So the system is specified by n coordinates qi, where I goes from 1 to n, and let the Lagrangian of the free system be written as half gij qi dot qj dot, where the dot indicates the total derivative of the qi and qj respectively. Gij is a second order tensor, which in fact is called the metric tensor and will be considered as symmetric, or is a function of the coordinates. Where gij is a function of the coordinates, and Further, they satisfy the condition that Gij into Gjk is to delta Ik. So we have distinguished here between the contravariant and covariant derivatives, and we have used the Einstein convention that any repeated index is summed over. Now, starting with this Lagrangian, we have to show that the equation of motion ensuing from this Lagrangian is given by Q I double dot is equal to gamma ijk qj dot qk dot, where gamma ijk are the familiar Christoffel symbols expressed in terms of the metric. The gamma ijk is half gij delta g jl by dqk minus gkl by dqj minus d, etc. Now the Lagrangian in this case is given as L is equal to half Gij into Qi dot Qj dot, where Gij is some kind of metric function which depends on the coordinates itself. So if we take the partial derivative of this Lagrangian with respect to Qk dot, we have the expression dl by d Qk dot is equal to half Gij delta Ik Qj dot plus delta Jk Qj dot, which can be written as half Gkj Qj dot plus Gik Qi dot. So, and dl by d Qk is equal to half Dgij d Qk Qi dot into Qj dot. See, the thing to remember, this is simple algebra. There is nothing very complicated. The only thing to remember is that the tensor G is a function of the coordinates, generalized coordinates, but not of the generalized velocities. So, we can then easily obtain the partial derivative of L with respect to the generalized kth generalized velocity, and then the equation of motion ddt of dl by dq dot is this expression in the equation of motion is equal to what is shown here in the slide is half times gkj qj double dot plus gik qi double dot plus half dgij dk ql dot qj dot, and likewise dgik dk qi dot qld. And using the Lagrangian equation then, and the fact that the metric tensor is symmetric, that gij is equal to gji, we obtain gik qi double dot is equal to half partial derivative of gij with qk into ql dot qj dot and two similar terms, and multiplying both the sides by the tensor G with indices k and p and summing over k, the left hand side is simply gik gkp ql double dot, which is equal to delta lp qp double dot. In the second term on the right hand side, the index L is dummy and we can replace L by J. We thus get qp double dot is equal to half times gkp dgij dqk minus dkg dqk minus dgik dqj, and the whole thing multiplied by qi dot qj dot. We define the indices, and this can be written in the form that qi double dot is a half gil partial derivative of gjl with dqk minus dgkl by dqj minus dgik dql multiplied by qj dot qk dot, and which is the desired result. And in fact, the term within the brackets is the familiar Christoffel symbol. Now let us consider the case where a particle is moving in a central potential u, which is given by as 1 upon r multiplied into 1 plus r dot square by c square. That is, the potential depends on the velocity. Now let us consider in the spherical polar coordinates, the Lagrangian is given by L is equal to half m r dot square plus r square theta dot square plus r square sin square theta phi dot square minus u of r. Now, given the Lagrangian and given this specific form of the potential, we have to obtain the Hamiltonian and the Hamilton's equations of motion, and we have to find out what are the constants of motion. The first thing to notice is that the phi does not occur in the Lagrangian. So phi is a cyclic variable and the momenta conjugate to phi is conserved. Therefore, p phi, which is the partial derivative of L with respect to phi dot, is equal to mr square sine square theta phi dot square is conserved. The momentum conjugate to the coordinate r is pr, which is equal to dl by dr dot, is then equal to mr dot minus du by dr dot, is, and using the expression for u, this is equal to m minus 2 by rc square, the whole thing multiplied by r dot. And likewise, the momenta conjugate to the coordinate theta, p theta, is mr square theta dot. Now the Hamiltonian H can now be written, because H is simply PRR dot plus P theta theta dot plus P phi phi dot minus L. Now substituting for PR, P theta and P phi from what we have obtained earlier, we write this Hamiltonian as half m r dot square plus r square theta dot square plus r square sin square theta phi dot square minus r dot square by rc square plus 1 upon r, which now we write in terms of the conjugate momenta instead of the generalized velocity using relationship, and the Hamiltonian then in terms of conjugate momenta becomes half pr square divided by m minus 2 by rc square plus p theta square by 2m square plus p theta square by 2m square sine square theta plus 1 upon r1 minus r dot square by rc square. And the Hamiltonian equations are then r dot given by dh by dpr, which is pr by m minus 2 by rc square, and theta dot likewise is p theta by mr square, and phi dot, which is given by dh by dp phi, becomes p phi by mr square sine square theta, and pr dot is minus dh by dr, is given by the expression here, and likewise p theta dot and p phi dot, and p phi dot is obviously equal to 0. The next problem we consider is the problem of a particle which is moving in a potential u of q is equal to exponential minus u q by q. Is like a Yukawa potential. And let's consider the case where the particle is moving in one dimension. Then for a one-dimensional motion, the Hamiltonian is simply equal to p square by 2m plus the potential energy u of q. Now, we can easily obtain the Hamiltonian equations from the Poisson equation, and would like to see how the solution is to be obtained. That in terms of the Poisson bracket, the equations of motion are, as we have seen in the earlier unit, p dot is equal to the Poisson bracket of p with h, and q dot is the Poisson bracket of q with h. So all we have to do is to evaluate this Poisson bracket of p and q with respect to h, where h is given as p square by 2m plus u. So for example, the Poisson bracket of p with h is the Poisson bracket of p with p square, and the Poisson bracket of p with u. The Poisson bracket of p with p square vanishes. So we need to evaluate only the second term on the right hand side, the Poisson bracket of p with u and u of q, where u of q is explicitly given in terms of q. So this is equal to dp by dq minus du by dp minus dp by dp this. So which is, as I said, is simply given by since dp and d they vanish, so you have the Poisson bracket equal to minus or minus mu e to the power minus mu q by q minus exponential minus mu q by q square. So we obtain, using the Poisson bracket, the time derivative of the momenta p dot is with exponential minus mu cubed by q multiplied by mu plus 1 upon q, and the time derivative of the coordinate q, that is q dot, which is given by the Poisson bracket of q with h, can be easily calculated, and we obtain q dot is equal to p by m. Thus q double dot is p dot by m, and p dot obtained earlier. Therefore, q double dot is exponential minus mu q by mq multiplied by mu plus 1 upon q. So this is the equation of motion we have obtained. Now, in order to solve this equation, let us multiply this equation by 2 q dot on both sides. So on the left hand side, we have 2 q double dot, which is the total time derivative of q dot square. On the right hand side, we have 2 by m exponential minus q by q into mu plus 1 by q dot, which can also be written as 2 by m a time derivative ddt of q dot square into e to the power minus mu q by q. So we have now this equation which can be easily integrated. So we get q dot square is equal to minus 2 by m exponential minus mu q by q is constant. As a final example, we calculate the Rauthian for a system whose Lagrangian is given by half m r dot square plus r square theta dot square plus r square sin square theta phi dot square minus v of r. So the potential depends only on the coordinate r, and we don't have any dependence on phi, so phi is a cyclic variable. So the Rauthian is obtained by eliminating the cyclic variable. From the Lagrangian, we have p phi is equal to dl by d phi dot, that is momenta conjugate to the cyclic variable phi is mr square sin square theta phi dot. We have phi dot in terms of p phi by mr square sin square theta. Therefore, the Rauthian is given by p phi dot minus L. So substituting for phi dot from there, the Rauthian is 1 by 2 p phi square by mr square sin square theta minus half m r dot square plus r square phi square plus vr. So it behaves like a Hamiltonian for a cyclic variable phi and as a Lagrangian for the other variables r and theta. As a final example, we have the Hamiltonian of a simple harmonic oscillator as h equal to p square by 2m plus half m omega square x square. Now we define the complex quantities a is equal to under root of m omega by 2 multiplied by x plus ip by m omega and its complex conjugate. And the problem is to write down or to express the Hamiltonian in terms of these complex quantities a and a star and evaluate the Poisson bracket between a and a star, between a and h, and a star and h, and to obtain and solve the equation of motion for a and a star. From the definition of a and a star, we have x is equal to a plus a star by under root 2 omega and p is equal to minus I omega a minus a star. Now, substituting for these in h, so h can be written now in terms of only a and a star because we substitute for x and p in terms of a and a star. So h simply becomes omega times a star a, and a very simple form. And the Poisson bracket of a with a star is very easy to calculate. Is the partial derivative of a with respect to q multiplied by the partial derivative of a star with respect to p minus the partial derivative of a with p multiplied by the partial derivative of a star with q, which can be easily seen to be equal to minus I. And likewise, the Poisson bracket of a with h is very easy to obtain because h is omega a star a, and from the property of the Poisson bracket of a with h is simply equal to omega a times the Poisson bracket of a with a star, which is equal to minus, and therefore the Poisson bracket of a with h is minus omega a, and Poisson bracket of a star with h is minus I omega a star. And the equation of motion in terms of Poisson bracket, which is p dot is equal to minus dh by dq is equal to the Poisson bracket of p with h for the variable a. A dot is equal to the Poisson bracket of a with h, which is minus I omega a, and therefore the a dot is minus I omega a, and therefore a is equal to a. The solution of this is simple. A is equal to a times some constant times e to the power minus I omega t, and similarly for a star. So it's in terms of a and a star, the Hamiltonian takes a particularly simple form, and the equations of motion are very simple and can be easily integrated. So let's summarize what we have learned. So what we have learned is that, in fact, what we have learned is to use the formalism which we learned in the last unit. And we have illustrated the Hamiltonian and Poisson bracket formalism here with the help of some representative solved problems. So what we have learned is to use the Hamilton and Poisson bracket, which we discussed in the last unit, and with the help of some problems, we saw how to use that.